Thermodynamics. Thermodynamics. Determination of latent heat. Determination of latent heat. Take a clean and dry calorimeter. Take a clean and dry calorimeter. Determine its weight along with stirrer. Determine its weight along with stirrer. Take some water into the calorimeter and measure its temperature. Take some water and measure the temperature of water and calorimeter and find the weight once again. Find the weight once again. Then prepare steam using a steam generator. Prepare steam using a steam generator. The figure shows a steam generator. In this, we notice a cylindrical vessel to which a rubber cork is fitted, which contains two holes. Through one hole, we keep a thermometer, and through the other hole, a wool packet tube is fitted. The bottle is filled with water and it is heated using a Bunsen burner. When the water boils, the steam comes out through the tube which is packed with wool, and this tube is connected to another steam trap in which the condensed steam will come out through one outlet and dry steam comes out through another outlet. The calorimeter with water is kept under steam trap and steam is collected into the calorimeter such that the temperature of the water rises by 5 degrees centigrade. And then the calorimeter will be removed and the contents are stirred well. The contents are stirred well. The temperature of steam is noted. The temperature of steam is noted and the resultant temperature of the water in the calorimeter is noted. The temperature of the steam and the resultant temperature of the contents in the calorimeter are noted once again. The resultant temperature is noted. The weight is measured once again. The resultant temperature is noted. The weight is measured once again. The readings are tabulated as follows. Mass of calorimeter with the stirrer is W1. Mass of calorimeter with the stirrer is W1. Mass of calorimeter with water is W2. Mass of calorimeter and water is W2. Mass of calorimeter with water is W2. Initial temperature of water is T1. Initial temperature of water is T1. Temperature of steam is T2. Temperature of steam is T2. Resultant temperature is T3. Resultant temperature is T3. Weight of calorimeter plus water plus steam is W3. Weight of calorimeter plus water plus steam is W3. Derivation of the relation for calculating latent heat of steam. Derivation of the relation for calculating latent heat of steam. Let us first calculate heat loss. Heat lost by steam. This is lost in two processes. One is when steam is converted into water, and then the temperature of hot water, it falls from 100 degrees T2 to T3. T2 to T3. So, in two processes it loses heat energy. The heat lost during phase transition Q1 is equal to the heat loss during phase transition Q1 is equal to W3 minus W2 into L. W3 minus W2 into L. W3 minus W2 is mass of steam and L is the latent heat of steam. The heat lost when the temperature falls to T3 from T2, it is given by Q2. Q2 is equal to W3 minus W2 into SW into T2 minus T3. W3 minus W2 into SW into T2 minus T3. Q2 is equal to W3 minus W2, W3 minus W2 into SW into T2 minus T3. Heat gained by calorimeter Q3 is equal to W1 into S into T3 minus T1. W1 into S into T3 minus T1. Heat gained by water Q4 is equal to Q4 is equal to W2 minus W1 into SW, W2 minus W1 into SW into T3 minus T1 into SW into T3 minus T1. But from calorimetry, we have heat lost is equal to heat gain. From calorimetry, heat lost is equal to heat gain. Therefore, Q1 plus Q2 is equal to Q1 plus Q2 is equal to Q3 plus Q4. Q3 plus Q4. Q1 plus Q2 is equal to Q1 plus Q2 is equal to Q3 plus Q4. Q3 plus Q4. Substituting the values of Q1, Q2, Q3, Q4, we get W3 minus W2 into L, W3 minus W2 into L plus W3 minus W2 into SW into T2 minus T3, W3 minus W2 into SW into T2 minus T3 is equal to W1S plus W2 minus W1 into SW, W2 minus W1 into SW whole multiplied by T3 minus T1, T3 minus T1. Therefore, L is equal to W1S plus W2 minus W1 whole multiplied by T3 minus T1 minus of W3 minus W2 into SW into T2 minus T3, W3 minus W2 into SW into T2 minus T3 whole divided by W3 minus W2, W3 minus W2. Using this equation, we can determine the latent heat of steam. Second law of thermodynamics. Second law of thermodynamics. This law expresses one of the properties of nature, which is heat cannot flow by itself from a body at low temperature to a body at high temperature. Heat cannot flow by itself from a body at low temperature to a body at high temperature. This fact is expressed in several ways and is second law of thermodynamics. And it is second law of thermodynamics. To express this, first we need to understand a heat engine. A heat engine is a device used to convert heat energy into mechanical energy. Statements of second law of thermodynamics. Clausius statement. It is impossible for a self-acting machine unaided by external agency to transfer heat from a body at low temperature to another at a higher temperature. This is Clausius statement. The second law of thermodynamics is also stated by Kelvin, which is known as Kelvin's statement. This states like this: it is impossible to derive continuous supply of by cooling a body to a temperature lower than that of its surroundings, the coldest of its surroundings. It is impossible to construct a heat engine operating in a cycle to convert heat energy completely into work without any change of the working substance. Generally, heat energy will be converted into work. While doing so, some heat energy is wasted. We cannot convert the entire heat energy into work. This is stated like this: it is impossible to construct a heat engine operating in a cycle to convert the heat energy completely into work without any change of the working substance. To understand this statement, we have to study the heat engine and its working. A heat engine can convert a fraction of heat energy into work. This fraction is called efficiency. Violation of second law means continuous extraction of energy by cooling the bodies. Violation of the second law says that it is not possible to extract energy by cooling the body to a low temperature than its surroundings. In a heat engine, we notice a source at a temperature T1 and a sink at a temperature T2. To understand this, let us take the working of a steam engine where coal is burned to obtain heat energy and it is used in boiling water. Steam will be generated, and when this steam is compressed, it gives high pressure. Using this pressure, the piston will be moved and thereby mechanical work is done. Then the temperature of the steam will be cooled to T2 degrees centigrade by exposing it to the atmosphere. Like this, a heat engine works. So let us suppose a source, that is high temperature source, is at T1, and from this source the heat energy absorbed by the steam is say Q1, and in pushing the piston, the work done by it is say W. The work done by the piston is W. Then when it is kept in contact with the surroundings, the heat energy given to the surroundings is say T2. This is at low temperature T2, that is known as sink. Then the steam comes to the original state. So once again this cycle will be repeated. So let us suppose that heat absorbed by the steam is Q1 and heat rejected to the surroundings is say Q2. Then work done will be equal to Q1 minus Q2. Q1 is heat absorbed, Q2 is heat rejected, and work done is Q1 minus Q2. Efficiency is work done by heat absorbed, W by Q1. Efficiency eta is equal to W by Q1, but W is Q1 minus Q2, hence eta is equal to Q1 minus Q2 by Q1, which is equal to 1 minus Q2 by Q1, 1 minus Q2 by Q1.